Hi, I'm Chris Brown, and this is the 7th module in a series on an introduction to axiomatic design, which is intended to be a separate part, or an independent part of a larger class course on axiomatic design and manufacturing processes here at Worcester Polytechnic Institute, where I am a professor in the mechanical engineering department. So for the next about 15 to 20 minutes, we are going to be looking at axiom 2. We've spent most of the time so far with axiom 1. And we'll take now a look at the second of the two axioms that Nam Su developed for design. So, to quote Nam Su from his 1990 book, Principles of Design, all the designs that satisfy the independence axiom, among those, the one that possesses the least information is the best. So essentially, if we can produce a diagonal matrix, and we'll be looking more at matrices and how to manipulate these in future modules, among those that can satisfy the independence axiom, essentially equivalently, which one do we want to go with? And that is the one with the least information. Now, information, a few questions come to mind. What is information when we talk about information content? Now, so reducing information often seems counterintuitive. Geez, I would like more information to be able to do a better design. But that's not the information content that's in the design. The information content essentially relates to the probability of success. So let's think of this intuitively, but in another way. Suppose that I need you to make something. And if I have to give you lots of instructions in order to make it, or more instructions to make it, the chance that you will forget one or misinterpret one goes up with the number of instructions that I give you. So in this sense, increasing the information content in this design, in this, say, process design, I'm trying to get you to make something, reduces the probability that it will be successful. So, for a design to possess or contain information means that there are essentially some set of more precise or demanding criteria or complexities that decrease the probability that that will work. Now, if we're thinking about production, for example, and you're going to make something, say, on a hand lathe, now, then the information that you need to transmit essentially to the machine to get the shape on the part that you want, since you're manipulating everything by hand, is much higher because it's much more, say, prone to error than if you're using a CNC machine tool where it can be programmed in, you can verify the program, and then essentially every time it should faithfully transmit that. So information in transmission reduces the probability of success because of the risk of the failure of the transmission system. So how can the information content be quantified? Well, we'll look at that in a moment. So compliance with axiom 2, the information axiom, should ensure that the design will be the most robust possible. A design with less information, as we said, will work more often, and therefore a production system, for example, would have a greater yield. So reducing the information content in design reduces the complexity and the uncertainty about its operation. And if we reduce the information content, that's going to increase the probability of success. And so we can quantify the information as information is equal to the log over 1 over the probability of success. So, if the probability of success were to be 1, then 1 over 1 is 1, and the log of 1 is 0. So that would mean there is no information content, and the probability of success is essentially 100%. So let's think about axiom 2 if we're trying to get from Worcester to Boston. Now somehow the Massachusetts Turnpike misses Worcester, the second biggest city in the state, the second biggest city in New England. So the major east-west road in Massachusetts avoids the second biggest city in Massachusetts. So to get from Worcester to Boston, you have to take several different interstates, find exits, and at least 2 different interstates, and find the right exit and get on going the right way. So each of these sort of transmissions of information has a certain probability of success. So if we were to imagine that we were having, say, a conference in Worcester and had to direct everybody to the airport in Boston, would we choose the shortest route, which might require finding several different turns, or the simplest route and maximize the probability of success? And so if we think about the number of people who might get lost and miss their flights as they're trying to figure out why 190 and 295 and 3 something all change numbers in different places, and why to go one way you get off in a different direction, and anyway. So think about giving directions in terms of axiom 2. That sort of provides us with an intuitive sense. In many ways, it's probably easier to think of axiom 2 in terms of just the probability of success. Now, the success here is in fulfilling the functions. So what is the probability? That's what defines success of a design, is that the functions are fulfilled. And that's essentially the objective of axiom 1. So axiom 1 offers a particular approach to a kind of subset of axiom 2, and that's why we look at axiom 2 separately. Axiom 1 is like a particular case of axiom 2, you can think of it that way. So what we're doing in axiom 2 is reducing the uncertainty in design by utilizing essentially known capability. Minimize the possibility of errors, minimize the impact of wear and other variables, and get a robust design, one that's apt to function successfully more often. Now sometimes we have a design that just has a single FR and single branch, in which case, if we only have one FR, then the only axiom we're concerned with is axiom 2. So as we said, if axiom 1 is satisfied by several designs, then we use axiom 2 essentially as a selection criteria to minimize, find the one, select the one with the minimum information, the one that possesses the least information or the greatest probability of success. All right, let's take an example then of a clamping mechanism. So here we have schematically represented a clamp, and this is intended to provide a load across an interface between 2 plates, which are represented here by 3 vertical lines. And so this is a kind of cam system, which is represented by this oval, and in one position the load is relieved and the 2 plates can slide back and forth. And then the other position, we've essentially stretched a linear spring, and we've stretched it by the amount of sort of the major minus the minor axis, and we have a displacement x. So the FR is to provide a certain clamping force. Now here you notice that we've used a shorthand sort of notation. So while the FRs should begin with verbs, in this case the provide is understood. And we're able to indicate that there's a tolerance on the FR, plus or minus a certain force. Minus, on the low side, it's got to be at least enough to keep these plates from sliding, and on the high side, it has to be small enough not to cause excessive wear or to break something. So So the relationship between the dp, which is the displacement, and the fr is just as a linear spring indicates, F equals kx. So one of the questions that we could ask, so this is a 1fr design. So what do we want for the linear spring? Something stiff or something soft? So a stiffer spring for the same displacement would provide a greater load. And sometimes it's appealing to think that that is what we would want. But let's see how this works out. And I would like to say that initially that was what I thought as well. So here's a way of representing FRs and DPs in an FR-DP space. So the FR is on the vertical axis, in this case it's force, and the tolerance is shown here by two lines perpendicular to the vertical axis, parallel to the horizontal axis. The axes in this case are perpendicular because there's one dp that's influencing one FR. So the two forces, or the two springs rather, can be represented by K1 and K2, K1 being the stiffer spring with a steeper slope. And so what we can do then is see where the tolerance on the FRs intersects with this description of the relationship between the FR and the DP, which is essentially the slope here, is indicated by the lines K1 and K2. So what we can see then is the way that tolerance and force translates directly and simply to a tolerance in the dp, from a functional tolerance, which is provide the force, to a physical tolerance, which is what we can have for x. And so what we notice here is that the softer spring, K2, results in a larger design range and lower information, therefore. In other words, with a larger tolerance of x, there is a greater chance that we will be able to hit that target and be within that tolerance, even if something in the manufacturing process changes, or the temperature changes, so the size of these elements changes, or say due to wear of the cam over time, we'll have a better chance of staying within the tolerance for the x. So this can be a metaphor for different kinds of stiffness, and so what we want to look for here is the lowest allowable stiffness. So why wouldn't you go with an enormous spring that was very soft, and then you would have a huge tolerance? In this case, you'd need a huge cam, and so we would certainly exceed some sort of constraint if this were to be, say, a feature on a chair. So we would want the whole system to be inside some reasonably sized package. So we would have a constraint about how big can this cam spring lever system be, and then I'll use the softest, or use the softest spring, which would be the largest spring, that would be consistent with that constraint. So this reducing the stiffness then allows for variance in manufacturing, as I mentioned, wear and temperature change. Also can accommodate impacts better. Softer springs, when you hit them, respond with less force. Another point here is that the information content can be used for improving yield in manufacturing, comparing delivery options, for example. What's the chance that there will be a snowstorm or a flight canceled so that the delivery won't be made? And we can take this, like in selecting the springs as we just saw, and we can use the same units, which comes from the probability of success, and we can put these into bits or bytes, which is what you get from taking the log of 1 over the probability. So when you do the problem, though, you want to take the same log base, either natural log, so it could be nats, or base 2, so it would be bits. And so in this case, all right, or in general, the information is defined as the log of 1 over p, where p is the probability of success. So essentially, The two axioms are intended to maximize the probability of success in satisfying the FRs. And we go through a kind of functional modeling to see if we're actually, how we're doing on that. And that's part of what the design matrix is about, which we'll develop further later. And then, and as we were just saying, the probability of success is directly applied in axiom 2. So a couple design that violates axiom 1 has a lower chance of being successful because the adjustment is difficult or impossible. So after we remove the coupling, satisfy axiom 1, so we get the independence, the probability of success then can be applied directly in axiom 2. Thank you very much for your attention.